Hello everyone. Am I audible? Hello. Am I audible? Okay. Hello everyone. My name is Ankit and welcome to day 2 of the session titled Introduction to Cryptography. So in this session, I'll just talk about the basics of model arithmetic. Yeah. All right. Sorry for the introduction. I'll be talking about the basics of model arithmetic. I'll be talking about properties and all that. And at the very end, I'll introduce to you a crypto system, which is called RSA. So let's begin. So what is model arithmetic? So let's say you have the basic arithmetic, which is uh, addition, subtraction, multiplication, and all that. But you have a condition, okay? And that condition is you have a limit or a cap on the maximum number that is possible. So let's say you add two numbers and then it goes beyond this limit. So what you would do is you would do an operation called mod. So what is the mod operation, you might ask? Mod is basically remainder. So what that means is you divide and take the remainder. Let's say, look at this expression right here. You have 14 and you have these three vertical lines and they're called, and it's what's called the congruent symbol. So you say 14 is congruent to 2 mod 12. So what this means is that the number 14 modulo 12 is the same value as 2 modulo 12. And you can apply this logic into real world scenarios. Let's say you have a clock and you have the time set in the 12-hour format. And you have, let's say, the current time being 11 p.m. And let's assume that 2 hours from now, what will the time be? Well, you wouldn't say 13 p.m., you would just say 1 a.m. So what actually happened there is that regular clocks work under model arithmetic because you only have these numbers from 1 to 12. Usually, I mean, that's not actual model arithmetic. Yeah. Okay, so I observed that there's a technical issue and I couldn't change the slide. Give me a minute. Give me 2 minutes. All right. Yeah. All right. Sorry about that. So as you can see, you have this particular symbol called congruent symbol, which is just three vertical lines. What it implies is that you have these two numbers on the LHS and RHS, and what it means is that these two numbers have the same value under modulo 12. So 14 modulo 12, when you divide by 12, you would have the remainder is 2. 2 mod 12 will also be 2. So they're the same, they're equivalent, but not equal. All right. And I mentioned about how clocks work, right? If you have the current time being 11 p.m. and you add 2 hours, it would be 1 a.m., not 13 p.m. That doesn't make sense. So let's continue. So I talked about the basic operations, right, under arithmetic. You have addition, subtraction, multiplication. Under modular arithmetic, what you would do is you would just perform these operations and then you would just take the value modulo n. And that would mean the remainder of that number. And another application is days of the week. So let's say you have the current day being Monday. So what day would it be 8 days from now? It would be Tuesday, right? Or let's say if it's Tuesday currently and 15 days from now, it would be Wednesday. Simple enough. We'll move ahead. So I mentioned how you can do addition, subtraction, multiplication under modular arithmetic, under mod. So what about division? So there is a concept in modular arithmetic which is called modular inverse. So let's say you want to find the inverse of a number a modulo n. So that's just all the numbers less than n from 0 to n minus 1. That's what it means. So the inverse of a would just be the particular value x such that a into x would be equal to 1 modulo n, obviously, as you can see on the screen. So it makes sense. Think about how additive identity works. The additive identity of a is just negative a because when you add a number with its additive identity, you get 0. So with multiplication under regular arithmetic, the inverse or multiplicative inverse of a would be 1 by a. Why? Because a into 1 by a is 1. Similarly, for under modular arithmetic, it's just the value for a such that when you multiply the two numbers together, you get 1 modulo n. So let's take an example, right? We have the number 3 modulo 7 and we want to find the inverse of 3. So what would we do in that case? We would find the particular number x such that 3 into x would be equal to 1 modulo 7. So whatever number it is, 3 into x, you take the remainder with 7, that number should be equal to 1. So since the mod value is just 7, we can try all the possible values, right? So let's try 1, let's try 2, 3 into 1 is 3, mod 7 is just 3, 3 into 2 in mod 7 is 6, 3 into 3 mod 7 is 3, 3 into 4 is 5, and 3 into 5 mod 7, 3 into 5 is 15, mod 7 is 1. So what we just found out is that the inverse of 3 modulo 7 is 5. because the product of these two numbers are 1 modulo 7. So that's how this is essentially division, right, under model arithmetic. So let's continue. I have a special challenge. I have this particular mod, which is 12, and I want you to find the inverse of 4. So what is the inverse of 4? The particular value x, such that when you multiply 4 with x, you get 1. So this challenge is open to you guys. If you could help me find out the value of x such that 4 into x is 1, please let me know. I'll give you 2 minutes. All right. So you might have noticed that this challenge is a lot harder than expected, right? So there's a particular criteria for when you want to find the inverse of a number. And that particular criteria is that the numbers a and b should be co-prime, as in they should not have any common factors. So we want to find the value of the inverse of 4 modulo 12. Well, what is the GCD, or greatest common divisor, of 4 and 12? Well, it was 4 itself. So the criteria was not satisfied. We can only find the inverse of a number if that number is co-prime with the modulus. In this case, it was not. So the answer is the inverse does not exist. So the inverse of 4 modulo 12 will not exist. And there's an important result. Okay. If two numbers have a GCD of 1, let's say a and b have a GCD of 1, meaning they're co-prime, no common factors, there is a particular identity. Okay. This identity is that you can find two numbers x and y such that a into x plus b into y is equal to 1. Now this particular identity, right, it's called Bazut's identity, and x and y in this case, they're called Bazut's coefficients. So the way you can find these two values x and y is with the algorithm called the extended Euclidean algorithm. And this particular algorithm is what is used to find the inverse. I will not get into how that exactly works, but that is the point. Okay, moving on from modular arithmetic, I want to introduce two concepts. This was actually brought up in the previous session, but I'll still reiterate. So crypto systems, right? They're basically just algorithms to encrypt and decrypt. You have a particular key size, you have the key, you have the encryption process, decryption process, things like that, signatures. So there are two main classifications for crypto systems. The two ones are symmetric crypto systems and asymmetric crypto systems. So symmetric, as you can guess from the word itself, symmetric implies that to encrypt and decrypt, you would use the same key. And there are examples of crypto systems that are symmetric, and they are AES and DES. And for asymmetric crypto systems, what it means is that to encrypt a message, you would use a particular key, and that is called the public key. And for decryption, you would use a separate key, which is actually private or secret. And that is called the private key, obviously. So you have a pair of keys, public and private, for asymmetric. And for symmetric, you have the same key. And for asymmetric, the examples are RSA and ECC. And ECC stands for elliptic curve cryptography. So that's enough about the categories of crypto systems. We'll actually get into one of them, which is RSA. So what is RSA? I'll give you an overview of what RSA is. So RSA is it is actually a very widely used public key crypto system for securing data, for encryption, decryption, and signatures. So this algorithm, right, RSA, was actually one of the first crypto systems or public key crypto systems, which implies that you have a public key and a private key, which was majorly used. TLS, which stands for Transport Layer Security, uses RSA. Yes, it was the first practical public key crypto system. It was widely used, and the name derives from the founders. You have Rivest, Shamir, and Edelman. They're the last names of people who founded, and their initials are contributed to the name, and they founded in 1997, and such that computers can't actually factor very large numbers, right? If you have a number which is composed of two primes, let's say P into Q, it's very hard for a computer to be just given a very large number and to factor it. So factoring large numbers is a computationally expensive problem. If you have a large enough number, it is very difficult to factor it. It'll take a lot of time. So that is the reason why RSA is secure. So let me go ahead and explain how RSA works. So to encrypt a message, right, there are multiple steps. I'll tell you the basics from the basics. So I mentioned factorization, right? We start with two prime numbers, P and Q, and it has to be very large. And if it is very large, it's hard to factor. That's why we choose large factors or large primes, obviously. And then step two is just finding the value n, which is equal to P into Q. And n is just the product of P and Q. And n has a different name, which is called the modulus. Okay. So you have two large primes, P and Q. You find n, P into Q. Simple enough. Next, we calculate what is called phi of n. This particular symbol, right, in step 3, this particular symbol is called phi. So what it means is that what phi of n actually is P minus 1 into Q minus 1. So why this particular number again? So there's significance for this number. Phi is basically the count of numbers less than n that are co-prime to n. So let's just get into your brain, okay? If you have a number n with two factors, P into Q, the phi of n would be P minus 1 into Q minus 1. And phi of n, which is called Euler's quotient, is just the count of numbers from 1 to n that are co-prime with n. All right. So, and the next step is we pick an integer e, which is part of the public key. Okay, it is available to the public. So yes. So I mentioned how there's a public key and a private key, right? So the public key would just be the number n and the number e. Simple enough. So again, we pick a particular number e, and there's a criteria too to pick the number e. This number e, right, should be between the values 1 and phi of n. All right. Additionally, this value of e should be co-prime with phi of n and also n. So we usually for encryption, right, we pick the number 65537 for different reasons. It's more secure and it's faster, but I won't get into why. So yes, that is e. And the next thing that we do is we calculate a value called d. Now, I mentioned how modular inverse works, right? So similarly, we just find d as the inverse of e mod phi. So e and d are inverses. So what would e into d mod phi be? It would just be 1. All right. So again, to reiterate, we have the public key, which is the value of n, which is the product of two primes. We have the integer e, which is just what's called the exponent. Okay, e is called the exponent. You have n and e as the public keys, and the private key is called d. All right, so we generated these numbers. Let me explain how encryption and decryption works in RSA. All right, so encryption, simple enough. You take your message m and you convert it to an integer. This is important. We convert it to an integer. And we also ensure that this value m is less than n. All right. So how do you encrypt? You take the value of m, you exponentiate it with the value of e, which you just picked out right now. And the result is taken modulo n. So we take the remainder with n. And that would be what's called a ciphertext. So given the ciphertext, which you commonly denote as CT, you might wonder, how do we decrypt it? And decryption is simple enough. We just exponentiate CT with D. So CT raised to D mod n would give you back the value of m. All right. So that is the process of encryption and decryption. Encryption is m raised to e mod n, where m is your message, e is the exponent, and n is the modulus. Decryption is just ciphertext raised to d mod n. That would give you back the message m. All right. Let me explain with a simple example. So for the process of explanation, I will pick very small values of p and q. This is very insecure, but yes, I'm picking the value of p as 5 and q as 11. So let's find the value of n. N is just the product of p and q. So in this case, n would be 5 into 11, which is 55. Next, we find phi of n, or the torsion function, the torsion value, which is just p minus 1 into q minus 1. So phi of 55 would be 5 minus 1 into 11 minus 1, which is just 4 into 10 or 40. Now we pick a value of e, which is between the value of 1 and phi of n, and we ensure that the GCD of e and phi of n is 1, meaning they're co-prime. So let me just pick the value of e as 3. So, all right. Now we find the value of d. D is just the private key, right? And as I told you, d is the inverse of e modulo 5. And that would imply d into e is 1 mod 5. So in our case, for e is equal to 3 and phi equal to 40, our value of d would be 27, since 27 times 3 is actually 1 mod 40. All right. So we are done with the key generation. We made the public key e into n, e comma n, which is 3 and 55. E is the exponent, n is the modulus, and the private key, which is just d. You might also write d and n together, it's fine. D is 27 and n is 55. So let's say you want to encrypt the message m equal to 7. Usually you want to encrypt, let's say, bytes, right? You want to encrypt a message. So what you would do is you just convert it to its integer form. So in this example, I'm taking a very small message. I'm just encrypting the number 7. Okay, let me go ahead and explain how it works. So we have the number 7. We raise it to e, and that is 7 raised to 3. And we take it modulo 55. So 7 raised to 3 is 343. We take the number modulo 55, which is remainder, when you divide by 55. And that number is 13. So the next step, so that's the ciphertext, right? C equal to 13. The next step would be decryption. So you have the ciphertext and you want to get back the message from the ciphertext. So how would you do so? You would just exponentiate your ciphertext C with the value of D. In our case, D was 27. So we'll just exponentiate 13 with 27. 13 raised to 27. And that number is too large. I couldn't fit it in the screen, but that's fine. And you would take that number modulo 55. And you will notice that you will get the message m equal to 7 back. So again, you might be wondering, if your ciphertext was very big and your D was very big, exponentiation is incredibly expensive. Even 13 raised to 27 is too big. Imagine you have you have a message with 100 digits, let's say. You want to decrypt it. Now that value will be so big, it'll not actually compute. So that is where a particular algorithm called square multiply algorithm comes into play. So the thing is, when you're exponentiating modulo a number, you can optimize it, right? You can make it faster. That's an algorithm which is called square multiply. So how it works is it essentially does repeated exponentiation and multiplication of the number 13. And then at every step of the way, you would take mod 55. So you wouldn't be left with a very large value and taking mod at the very end. That's very inefficient. So yes, I'm just mentioning how it's actually fast and optimal to run exponentiation on large numbers. So that's fine. We have the message back, m equal to 7. Yeah. Okay. So let me talk about the security of RSA. So RSA is actually widely used, right? It is used for signatures. Let's say you want to sign a message. There's a concept called digital signatures. What it means is that you verify the ownership of a message, or it's like a fingerprint, right? It's like a digital fingerprint. You say, or a signature, like an actual signature on a paper. If you have a message, you can tie your identity to the message. And that's the abstract idea of signatures. And it's also used for TLS, as I mentioned, which is a topic involved in web security. And RSA works because it is hard to factor large numbers. So if you picked a large enough primes P and Q, your n would be incredibly large and you couldn't factor it. So yes, uh, if your RSA setup, if your keys are weak, let's say your primes are too small, well, you can compromise it. You can just factor it. One of the major trends in computing is the emergence of quantum computers. So RSA is actually under threat of quantum computers because they can actually factor large numbers. And that is bad for RSA because if you factor the number n, you would get P and Q separately. With P and Q, you can find the value of phi. With phi, you can find the value of D for any E. And what would you have? You would have the private key. So yes, it is essential that your primes individually are hidden, not exposed in the public, and kept secret, and you just give the value of n and e to the public. So let me go ahead. Okay, let me talk about a few attacks on RSA. Well, I talked about how picking large primes are important. Well, if you have a large enough n and the factors of n, p and q are actually known to the public, it is the whole thing is compromised. You could decrypt anything. You could find the private key D by finding phi, and you could decrypt anything you want. So you don't want to leak your primes. Another attack is using a small value of E, which I will get into soon. And the next thing is Fermat's factorization, okay, Fermat's algorithm, right? Let's say you pick the value of n as P and Q, and P and Q are very, very close primes. So there is an algorithm called Fermat's algorithm or Fermat's factorization algorithm, which can actually factor your n if P and Q are very close to each other. So it's important that you pick them randomly and that they're not consecutive, right? It shouldn't be consecutive or close enough. And you have stereotype messages, CRT and RSA, which stands for Chinese Remedial Theorem, common modulus, Venus attack, Punadorfi. I will not get into all these, although I will mention Wiener attack, which is an attack where if your public exponent E is very large, your value of D would be quite small. And Wiener attack and Punadorfi are related to each other, and they work when your value of D is very small. And there are more attacks on RSA. I'm not explaining any of them because, again, it's not at the basic level. Again, okay. So I mentioned FactorDB. There is a particular website, okay, which is called factordb.com. So what it has is it has a very large database of uh, of numbers n and their factors. So it's just a big table, right? You have the number and its factors. So right. So I have a challenge for you. Try to find the factors of n1 and n2. They are on FactorDB on the website. And also, I have a particular ciphertext. I have a particular value of n and e. So what I want you to do is to factor this number n3, get the factors p and q, and try to decrypt the message where e equal to 6537. I'll give you 2 minutes. Okay, so I'll help you out. So let me take these values. Let me try to factor the value of n. My bad. All right. So the website name is FactorDB. Okay. This is what it looks like. You just input your number, and what it will give you are the factors of the number. So let's factorize. Okay, so as you can see, the factors of this particular number, which we picked for as n, are these two numbers. So let's copy them. I'll decrypt in front of you. I'll show you the steps. Okay. I'll just open up my terminal. Okay. Okay. These are my values of P and Q. Let's find the value of n, which is just P into Q. Now, you have to find the value of phi. Phi is just P minus 1 into Q minus 1. Give me a minute. All right, sorry for that. So these are the factors P and Q. We have n equal to P into Q, and phi would just be P minus 1 into Q minus 1. Okay, so the particular value of E in our case was 65537. I also copy the value of the ciphertext. I'll do that. So C equal to this very big number, right? So how do you find the private key? Your private key D is just the inverse. So the way you find the inverse in Python, right, under modulo n, is just you enter the number E, you enter minus 1, and you enter the modulus, in our case, which is just 5. So what that would give you is the inverse of E with respect to 5. Negative 1 implies inverse. Okay. So you have D. Now, the next step is just to find the message M. That is simple enough. You just exponentiate the value of C with D, and you do that under modulo n. All right. So M right here is our message. M is actually an integer, but the thing is, it's actually bytes represented in integer form. So there, I want to convert this back to bytes. So I would import a particular library called PyCryptodome. It has a function called long to bytes. So if I run long to bytes, what it will give me is the byte representation of this number. So let me go ahead, enter the number, and yes, that was the message. So what have we done right now? We have taken the ciphertext, we have decrypted it, we have attacked it. How? By factoring the value of n. If you didn't have the factors, you wouldn't find phi. If you didn't have phi, you couldn't find D. So yes, we've decrypted it. I will be continuing. Give me a minute. All right. So that was the first challenge. Let me go ahead. I'll now be explaining a particular attack. Okay, before I do so, does anyone in the audience have any doubts? If you have any, you can post them in the chat. I'll be getting back to you immediately. If there's anything with how the decryption worked, how key generation works, how encryption works, you can ask it out. Okay, so since no one had any doubts, I will be explaining a particular attack in RSA where you pick a small enough value of E. Okay, now it is important that we use a a large enough E, but not too small. Okay, if we use the value of E equal to 3, it is actually quite small. Okay, and if your value of E is 3 and your M is very small or smaller than the cube root of n, what would happen is that when you encrypt, right? Encryption is just m raised to e mod n. So if you encrypt m raised to e, that number would actually be less than n, right? We want our ciphertext to wrap around n as many times as we want. If your m is small and your e is small, in our case e equal to 3, if you find m raised to 3 and that is less than n, sorry, that would mean that the operation of modulo never applied on the ciphertext. So what you can do is just take the cube root, right? Or there's a generalized case, okay? If your value of m is just a little higher than the cube root of n, what would happen is that your ciphertext or your message would just be the ciphertext with a few multiples of n and its cube root, obviously the cube root of the ciphertext with just a few multiples of n. If that makes sense, that doesn't make sense, I'll repeat it again. So again, you want your message encrypted to be larger than n. If it is less than n, you can just take the cube root or the fourth root or fifth root, whatever it is. So it's important that that it is not the case. If your e is 3 and your m is less than the cube root of n, encryption would not actually make a difference. You could just find the cube root. Or if your m is just above the cube root of n and you exponentiate it, it would wrap around n only a few times. So your actual message would just be the cube root of ciphertext with k into n. All right, so that's small e. It's important to use a large enough e. We use the value of e equal to 65537 for a good reason, because it's optimized and efficient. Okay, I'll move on to the second and final challenge of the session. Okay, I have these three numbers, okay, E, ciphertext, and N. A particular message has been encrypted with E equal to 3. I want you guys to decrypt the message with the attack I mentioned just before. So, recollect what you have learned and try to decrypt your ciphertext. These numbers will be put in the chat. Okay, I can observe that a user named Ayushman or Ayush Sharma, okay, he has actually solved the challenge. So well done. Okay, for those of you who couldn't actually solve it, I'll explain how the attack works. It's very simple. Okay, so let me just take the value of the ciphertext. Give me a minute. Okay. Yeah. Okay, this is my ciphertext. I would like to try taking the cube root first and checking if if the cube root is actually perfect, right? If it's an actual integer and not a fraction. So you could actually just do c raised to 1 by 3, but I'm not going to do that. You might lose precision. So there's a particular library in Python called SymPy. Now, SymPy has a particular function called integer nth root. So I'll be using that. All right. So what integer nth root, this particular function, integer nth root, does is that it finds the nth root of an integer. Simple enough. So we just give the value of c and we give the value of n. So we want to find the third root, right? The cube root. So we give the second argument to this function as 3 and the first argument is the number itself. So what you can observe is that you get an output, right? So this number is your cube root and you have, it's a tuple, right? You have a second value which is true. True indicates that it was not a fraction, it was an actual integer. So yes, you can observe that the ciphertext C was a perfect cube and the value of n was too large, your m was too small, and your ciphertext actually never wrapped around the value of n. Okay, you have the value of m. So let me just type it out. Oops. My bad. Okay, let me just convert it to integer and we use the function long to bytes. It's very useful. And you get the message back. So yes. So that was it for this challenge. That was the small E attack. And that was actually the end of the session as well. So if anyone has any doubts, they can post it in the chat. Or any questions in general, not related to RSA, if they have any doubts on how the inverse is calculated, how model arithmetic works, things like that. Or CTFs in general, you can ask. Again, if you have any doubts regarding InCTF as well, InCTF-J, you can ask it in the chat as well. All right, someone has asked me how you calculate the inverse. So I'll go back to that particular slide. Okay. So if your number is very small, let's say your number is your modulus, sorry, if your modulus is very small, you could try all the numbers. That's inefficient, right? If your modulus is very big. So there is a particular algorithm, okay? That algorithm's name is the extended Euclidean algorithm. You can look it up. It's called EGCD. EGCD stands for extended GCD. So what it does is it takes your A and B. Let's say you want to find the inverse of A with respect to M. You would run this algorithm, right? EGCD algorithm on A and M. And what you would do is you would get the coefficients, right? You get the coefficients X and Y. And what you can observe is that if you give your number A and the modulus as B, your value of X would be the inverse of A. Simple enough. So to repeat, finding the inverse involves an algorithm called EGCD or extended GCD. You give the two numbers as A and your modulus B. Let's say your modulus is B. The particular value of X in that case would be your inverse. So that's how you find the inverse. So is that fine? Is that good enough? Okay, the thing is, finding the inverse, right? In this particular case, for decryption, right, you're finding the value D, right, which is just the inverse of E. Now that inverse is actually found with respect to phi. So the thing is, if you don't have the value of phi, if to calculate the value of phi, you need the numbers n, you need the numbers p and q. Without p and q, you can't calculate phi. Why? Because phi is p minus 1 to q minus 1. So again, I think the confusion here is that you might think that D is the inverse of E modulo n. It's not modulo n, it's modulo phi. So that's the key point of RSA, which is that to find the private key D, you would have to find the inverse modulo phi, which requires that you know the factors P and Q. So did that make sense? All right, that makes sense. Okay, are there any more doubts? Okay, someone has asked me how long to bytes actually works. So I'll explain how that works. Let me open up my terminal. Okay, so what long to bytes does is it converts your bytes to an integer. So how it actually finds it is that, let's say you want to find the bytes to long representation of a byte A. So what you would do is, a byte is 8 bits, and with 8 bits, you can have numbers from 0 to 255, right? So if, let's say you have the letter A has an ASCII value, or you represent A with the ASCII value, which you can find with CHR or ORD, my bad. Right, that's 97. So just finding long to bytes of A, my bad. Yeah, my bad. Bytes to long, my bad, my bad. I didn't import it, obviously. You would get 97, right? So if you have a very large message, okay, you asked for long to bytes, my bad. So what you would do is you would take the number, let's say a large enough number, let's say it's M. You would repeatedly divide with 256. You would take the remainder, and that remainder would be your very rightmost byte. So I'll demonstrate that. Shift C. Let's say you have M. Let's say you find the remainder modulo 256. Now that is 125. Now, what can you observe here? You can observe that the byte is the closing bracket, and that is the last byte. So you would continue this process, right? So what happens is that you take the modulo, how the function works in the interior is that you find the remainder modulo 256, and that is just this. And then you would flow divide M by 256. And then you would repeat the process, right? Control Shift C. Take the remainder mod 256, 51. Let's find what 51 stands for, which is 3. So you would keep doing this, right? You would keep finding the remainder mod 256. That would be the next bit from the right. You would divide by 256, and you go ahead until you exhaust all the values, until the value reaches basically 0. So that's how long to bytes works. Bytes to long is similar. You just take the ASCII value, or just it's just bytes, right? It has an integer representation for each byte. You would multiply it with powers of 256. So if your messages say ABC, what would happen, what you would do is that you would take the representation of C. I'm just writing it down, this is not actual code. You would multiply with 256 raised to 0 from the left, and then you take the representation of B in as an integer. You'd multiply with 256 raised to 1, and finally you would add with, for the byte A, 256 raised to 2. I can actually demonstrate this. Let's say you want to find the integer, which is just odd of A, odd of B. Now what this odd function does is it just gives you the ASCII value of a character. All right, and again, this is not the notation for exponentiation. That's XOR, my bad. Okay, you get this particular number. So let's test this, right? Let's try finding bytes too long for ABC. You would get the exact same value. So that's how it works. So yes. Yeah, I mean, yes, long to bytes does convert each letter to ASCII, but the thing is, it's not adding them together, right? You would convert to ASCII, you would exponentiate with 256 based on the position. It's like base 10. You have numbers base 10, right? Similarly, you'd think of that, but for bytes. That would be base 256. So you take the ASCII value for each letter in the position. You would multiply with powers of 256 based on the position. So if it's the rightmost letter, you would find the ASCII value, multiply it with 256 raised to 0. And similarly for the rest of the letters. Just like how you have the number 1, 2, 3 as 1 into 10 raised to 2 plus 2 into 10 raised to 1. 10 raised to 2, my friend. Plus 3 into 10 raised to 0. What did I do here? My bad. Right. So similarly, you just do the same thing for bytes. The base for bytes is 256 because each byte you can represent the numbers 0 to 255 with one byte. It's same logic. It's just base 256. Okay. Does anyone have any other doubts? All right. Is it possible that m is larger than n for standard RSA? Actually, no. There is a requirement that your value of m, right, your message should be less than the value of n. So the reason for that is it's fine if you pick a value m larger than n, but when you encrypt and decrypt, right, you would get the result of n modulo n, and you would lose data. So it's important that you pick two large enough primes, P and Q, such that your n is very large, and you ensure that your value of m is less than n. So yes, it is a requirement that your m is less than n. The thing is, if m is larger than n, which is modulo n, so you would actually lose data, right? Your m being larger than n doesn't help you. You would get only a part of that data, right? And you would actually not be able to recover your message back from that case, in that case, when you decrypt. All right. Are there any more doubts? Okay, if you're interested in trying out more crypto challenges, there is a very good website called Crypto Hack. It's called cryptohack.org. You can look it up. It has a lot of challenges from the very basic level. You can learn about RSA from over there. You can try RSA challenges. You can try simple challenges like ZOR or things like that. You can even get into AES, ECC. I mentioned that in the symmetric and asymmetric crypto systems, right? So yes, the website you should be looking at is what's called cryptohack.org. I think I'll type it in the chat. Yes, PicoCTF is a good example too. There's like an archive of challenges. You can try them. And similarly, you also have another website called CryptoPals. And what that has is you have implementation challenges, right? You have challenges where you have to implement or write code for crypto systems, right? So that would improve your programming skill as well. How do you know E is co-prime? Well, you pick E so that is co-prime, right? You as a key bearer, you would pick your N, you would pick your P and Q, and you'd have a phi, right? So you would actually pick an E which is co-prime to phi. You have knowledge of phi as the person who is generating your value of E. Are there any more doubts? All right. If there are no more doubts, I think we'll conclude the session. But again, I'd like to remind you guys that you should join the InCTF Discord, register for InCTF quals, and the qualifier is on 13th December. So there'd be a learning round and demo challenges as well on the platform. Okay, which will come about. So yes, the main thing is do join the Discord. We'll post updates over there. All right. So I think that's about it. I'll end the session. Thank you so much for joining. And I hope you learned something new. So yes.